They thought it would be quiet after the pass. In the early hours of December 20th, Earth watched in collective anticipation as 3i Atlas completed its closest approach. Observatories from Chile to Japan tracked the object with relentless precision, expecting signs of decay, fragmentation, or gradual exit from the inner solar system. Instead, the opposite happened. The moment it passed Earth, it began to change. It didn't slow down. It didn't lose cohesion. It didn't shed material like a typical comet under strain. It adjusted. There was no sudden burst, no violent tail eruption, no debris cloud. What followed instead was a series of subtle shifts, barely perceptible at first, but deeply unsettling in their implications. Course vectors recalculated, rotational patterns altered, tail signatures fluctuated, then reorganized. Something inside the object had reacted to its encounter with Earth, and the behavior that followed broke nearly every predictive model astronomers had in place. This isn't just another pass-by. It's a message. Because this isn't just a comet anymore. It never was. For the past several weeks, 3i Atlas has defied all classification, burning through the solar atmosphere without disintegrating, generating jets at unnatural angles, and emitting structured bursts of non-random frequencies. What passed Earth on December 20th wasn't just an icy rock from deep space, it was aware, and as the planet turned its attention away, relieved that the closest point had been reached, those still watching noticed something else. It was already turning back. This episode will walk you through what happened immediately after the Earth flyby, the change in motion, the structural reconfiguration, the unexpected retention of mass, and the sudden vanishing of certain emission lines, right before it released an energy pattern never seen before from any known celestial body. This isn't a comet leaving us behind. This is a system shifting its orientation, and for the first time, pointing somewhere else, maybe even back toward us. Let's begin. For months, scientists had circled December 20th on their calendars. It wasn't because of a launch, a solar flare, or a scheduled data release. It was because of a quiet passage, a calculated moment when an interstellar object would thread its way between Mars and Earth, crossing our observational line of sight without fanfare, without interference, just raw data and geometry. That object was 3i Atlas. And on the morning of December 20th, it made its closest approach to Earth. By astronomical standards, this wasn't close in the way the headlines might suggest. There was no risk of impact, no gravitational slingshot that would tug at our tides. Instead, the object passed just beyond the orbit of Mars, nearly 1.8 astronomical units from Earth. But in space observation, distance doesn't diminish importance, because this moment wasn't about physical proximity. It was about visibility, orientation, and interaction. It was about what would happen when the object moved from a position of observation into one of evaluation, where data from infrared, optical, radar, and radio telescopes could finally converge in real time. Everything leading up to this point had been building quietly. After its solar approach in late October and early November, 3i Atlas had done something that puzzled even the most conservative models. It had stabilized. Rather than fragmenting under the heat, it emerged intact. Rather than fading as it drifted away from the sun, it had intensified. Jets had formed, an anti-tail had appeared, and by the second week of December the object still showed signs of low-level emissions contradicting every thermal expectation for an outbound interstellar body. And now, as it passed Earth, those behaviours could be measured at unprecedented clarity. The night before closest approach, observatories across the globe went into coordinated lock. From Chile's high-altitude observatories to infrared networks in Hawaii and Japan, tracking systems began pulling composite frames. The James Webb Space Telescope reoriented for a short passive scan. Even older orbital telescopes normally relegated to planetary watch lists were repurposed for wide-angle dust trail captures. There was no panic, no rush, just precision. And in that precision, anticipation. At exactly EO 411 UTC, the object crossed its minimum observational arc, the moment when it was aligned at its closest observable distance from Earth. For 8 minutes on either side of that mark, instruments from 5 continents captured spectral bands in near-perfect overlap. What they found in that narrow window wasn't violent, it wasn't explosive, it wasn't even bright in a traditional sense. It was subtle, controlled, like a machine finishing its maneuver and coasting silently past its observer. There was no fragmentation trail, no thermal signature of internal collapse, no trailing debris arcs or unexpected venting. The coma remained symmetrical. The jets, previously angled slightly sunward, now aligned into a cleaner cone. The anti-tail, which had puzzled scientists for weeks, held its shape. There was no diffusion, just a faint glow curling back toward the sun, steady, quiet, geometric. At first, it seemed like the object was simply gliding past. But in the hours that followed, something in the data changed. The object was not departing on the expected vector. The arc was slightly off, less than a degree, less than 0.1%. But it was enough to tell scientists that what they had just observed was not just a passive body crossing Earth's lens. It was something active, something that at the moment of closest approach had chosen not to reveal itself, but had made one very specific decision. It had changed course. It began with a discrepancy, small, almost imperceptible, just a few pixels off from what the predictive software had projected. But in orbital mechanics, small errors carry weight. They don't vanish, they grow. And this one was growing slowly, silently, underneath the radar of most casual observers. It wasn't dramatic, not like a collision or a breakaway. It was just enough of a shift to raise the hairs on the necks of those who knew what to look for. At first, it came from one dataset, a passive radar scan from the Canada-France-Hawaii telescope. The team noticed that the object's outbound velocity vector no longer aligned perfectly with the inbound track. In isolation, that kind of error might have been dismissed. Noise, atmospheric disturbance, instrument drift. But within hours, reports started surfacing from 2 additional observatories in the southern hemisphere, both noting the same minor deviation. By the end of the day, 5 independent observation stations had confirmed it. 3i Atlas was not following its calculated exit trajectory. Now, this isn't the first time an interstellar object has exhibited a non-gravitational acceleration. Both Oumuamua and 2i Borisov showed slight deviations from projected courses, likely caused by outgassing or solar pressure. But those shifts had context. They made sense. In both prior cases, the accelerations were asymmetrical and messy, tied to irregular outbursts of gas and structural shedding. They looked like thermal reactions. This didn't. The data showed that 3i Atlas's deviation was clean, linear, purposeful. It didn't wobble, it didn't meander. It curved, subtly, gracefully, as if adjusting rather than reacting. The magnitude of the shift was less than 1 arc-minute. But the shape of it, that was what bothered analysts most, because it wasn't chaotic, it was modelled. It traced a new outbound path that was coherent across multiple scans, almost as if it had been planned. Orbital analysts at NASA's Jet Propulsion Laboratory began reprocessing the path. Using data from both ground and space-based tracking systems, they attempted to recreate the deviation using traditional explanations. First came the outgassing model, the usual culprit when comets accelerate unpredictably. But this time, it didn't add up. The direction of motion wasn't aligned with any observed jet vector. There was no thermal pulse, no lag, no rotation-induced wobble. The energy simply wasn't there to justify the change. Then came the solar radiation pressure hypothesis. In theory, intense sunlight could produce a sustained force on an object with a large surface area and low mass, a sort of photon sail. But that too began to break down under scrutiny. The object's orientation hadn't changed significantly, and solar pressure would have created a gradual drift, not a sudden pivot across a narrow window of hours. The anomaly remained. The shift occurred within 16 hours after closest approach, with the first measurable deviation noted just after the object passed the 1.9 AU mark. It was as if 3i Atlas had waited until it had cleared Earth's field of vision before gently altering its course. The direction of movement wasn't entirely random either. It was angled slightly away from both Earth and the Sun, placing it on a new outbound arc, still hyperbolic, still escaping, but not quite in the way we expected. The scientific term used for such motion is a non-gravitational vector impulse. In natural objects, it's chaotic. In 3i Atlas, it was symmetrical. That's the difference. And it's that difference that triggered quiet conversations in back rooms of astrophysics departments and orbital observatories around the world. Not because anyone knew what it meant, but because for the second time in just a few months, a visitor from another star system had done something that shouldn't have been possible. And this time, Earth was watching. When a comet ejects material, it does so because of heat. As the surface absorbs solar radiation, the ice sublimates, turning directly into vapor. That vapor escapes through cracks and fractures, dragging dust along with it, creating the familiar tails and flares we associate with comets. And every one of these emissions, from the smallest jets to the longest ion trails, follows the same fundamental rule. It moves away from the heat source. But on December 20th, shortly after 3I Atlas passed its closest point to Earth, something appeared that broke that rule entirely. At first it was faint, almost mist. In the mid-infrared range, a concentrated jet emerged near the southern quadrant of the object's nucleus. It wasn't a general venting or a diffuse outgassing cloud. It was a directed stream, tightly collimated, with a consistent vector and high symmetry. Telescopes in Chile and Japan confirmed it within minutes of each other. It wasn't a glitch. But the real shock came when its direction was calculated. The jet wasn't escaping from the night side of the object, the side facing away from the sun, as models would predict. Instead, it was angled directly back toward the solar vector, the very path from which it had just come. A jet, erupting toward the sun. In comet physics, this is nearly unthinkable. Everything about sublimation depends on thermal gradients. Material escapes from sunlit surfaces, not shaded ones. The heating is always asymmetrical, and the pressure differential forces gas to vent in the opposite direction. A jet that points into the heat source is functionally impossible unless something is actively shaping it. So scientists began looking for explanations. Some suggested a rotational lag, that perhaps 3I Atlas had spun on its axis and exposed a previously sunlit surface. But this would require the object to rotate quickly, and every previous observation had indicated a very slow spin rate, likely less than one full rotation every 18 hours. That didn't match the timing. Others proposed a surface collapse. A crust of dark material might have cracked, exposing a volatile rich layer underneath. But again, the direction of the jet didn't fit. The crack would have needed to form on the solar-facing side and then somehow redirect material against the flow of thermal pressure. None of the natural models worked, and as the hours passed, the structure of the jet only made things stranger. The material didn't just vent and fade, it maintained coherence, holding its column shape as it extended thousands of kilometers from the nucleus. Multiple frames showed the jet brightening, then stabilizing, as if it had reached a controlled output level. The edges were clean, the density gradient was uniform. This wasn't a spray of particles, it was a beam. The implications of that were chilling. In traditional propulsion, whether chemical or solar, the easiest way to generate forward movement is to expel mass in the opposite direction. Newton's third law: push backward, go forward. And in this case, if 3I Atlas were to want a directional change, perhaps away from Earth or away from the Sun, a jet oriented backward along its inbound path would be the precise maneuver required. Suddenly, the anomalous post-flyby deviation had a partner, a physical impulse, caught on camera, pointing exactly where it needed to. Was this just exotic comet behavior? A type of internal venting never before seen in any solar system object? Or was it something far more sophisticated, a propulsion-like system using natural-looking jets to apply fine-tuned motion? Astronomers weren't saying that out loud, but in the tracking logs the jet was catalogued with a simple but unsettling label: vector consistent, direction sunward, duration active, and just below that entry another line appeared: possible navigational function. Tails are how we recognize comets. Bright luminous trails that stretch out behind them, always away from the sun, shaped by solar radiation and the continuous pressure of the solar wind. It's one of the first things students of astronomy learn. A comet's tail doesn't follow its path of motion. It points directly away from the sun, no matter which way the comet is actually moving. It's reliable, predictable, universal, until it's not. Just over a day after 3I Atlas passed its closest approach to Earth, several observatories, including 2 in South America and 1 on the Canary Islands, began reporting something that shouldn't exist. At first it was dismissed as noise, a miscalibration, perhaps an atmospheric reflection. But as more independent datasets rolled in, it became undeniable. A new feature had emerged behind the object, and it wasn't behaving like a tail. It was pointing toward the sun. The anti-tail was back. This wasn't the first time observers had seen this with 3i Atlas. During its earlier solar encounter, it had briefly displayed a tail-like structure that appeared to stretch back toward the sun, a phenomenon dismissed at the time as an optical illusion, the result of dust trails lying in the orbital plane and viewed from just the right angle. A perspective trick, a line of previously shed material catching sunlight from a distorted vantage point. But now, Earth and 3i Atlas were in an entirely different geometric alignment. The angles had changed, the lighting had changed, and yet the anti-tail remained, forming a sharp, narrow column extending in the exact opposite direction expected. This wasn't a trick of the eye. It wasn't a misalignment of Earth's position. The anti-tail had become structural. It shimmered faintly in the visible bands but radiated more clearly in the ultraviolet, picked up most strongly by a telescope network in the Indian Ocean. The material appeared to be dense, particulate, but well organized. It didn't disperse chaotically like dust typically does. Instead, it formed a fine line, narrow in angle but long in reach, extending tens of thousands of kilometers back toward the sun. And perhaps most disturbing of all, it didn't move. Over several hours of tracking, the anti-tail retained its shape and direction, with a kind of stability no natural comet dust has ever exhibited. No bending, no trailing curvature, just a rigid orientation, as if being pulled by, or resisting, an unseen force. Some researchers suggested it could be an active thrust vector, similar to the sunward jet observed a day earlier. If true, that would mean the anti-tail was not a legacy dust trail or an artifact of orbital geometry, but a consequence of the object's behavior, a byproduct of directed emission or propulsion. Others considered it might be a field alignment effect, perhaps dust suspended within a magnetic or electrostatic structure. But for that to occur, 3i Atlas would need to be producing a localized field strong enough to stabilize particulate matter across vast distances. No known natural comet has ever done that. To make matters even stranger, brightness variations were observed along the spine of the anti-tail, periodic pulses that suggested internal dynamics. Not only was the structure persistent, it appeared active. For the observers tracking it in real time, this wasn't just an optical anomaly. It was a signal, a recurring motif in the behavior of 3i Atlas, one that contradicted comet logic and instead hinted at orientation, as if the object wasn't just reacting to sunlight but coordinating around it. In the official logs, the anti-tail reappearance was classified as persistent anomalous structure, a term designed to sound neutral. But behind the scenes, scientists were struggling with a much simpler term, direction. Because the only thing more unnatural than a tail that points toward the sun is one that doesn't waver. There was no flash, no explosion, no electromagnetic spike, just a slow, silent drift upward in brightness, subtle enough to be missed by casual observers, but unmistakable when stacked against baseline readings. As 3i Atlas moved further along its post-Earth trajectory, a curious phenomenon began to emerge across multiple spectrums. The object was getting brighter. This wasn't supposed to happen. Comets brighten as they approach the sun. That's the rule. As solar radiation increases, surface ices vaporize, jets form, particles scatter, and the overall luminosity climbs. After perihelion, the point of closest approach to the sun, that process reverses. With less energy input, the activity drops off, and so does the brightness. Comas shrink. Tails fade. Infrared signatures cool. The comet coasts outward, spent and silent. But that's not what happened with 3i Atlas. Instead, the object, having already passed both the sun and Earth, began a slow increase in luminosity across the visible and near-infrared bands. The data came in from telescopes in Arizona first, then from optical sensors in Eastern Europe, and finally from space-based infrared arrays aboard the NOAA satellite grid. All showed the same pattern, a gradual rise, not dramatic but sustained. Even more unsettling was the timing. The brightening began roughly 12 hours after the anti-tail re-emerged. It didn't match the sun's rhythm, it didn't align with a flare or solar wind spike, and it certainly didn't follow any rotational modulation pattern. Instead, the increase was steady and uniform with no atmospheric volatility or chemical noise, like a system warming up, not from external heat, but from within. So what was causing it? The surface temperature of 3I Atlas, as measured by infrared thermometers, remained constant. There was no influx of solar energy, no thermal jump. The coma was stable. Outgassing had diminished. There were no observable new jets. And yet, the nucleus began to glow more strongly, as if an energy reservoir had been activated beneath its crust. Some suggested it might be the result of internal heat migration. A delay in how thermal energy absorbed during perihelion was moving outward. But that model required the object to have a very specific composition and insulation profile, essentially a hollow interior, rich in low-density volatiles and wrapped in a heat-trapping shell. Possible, yes, but statistically unlikely. And it still didn't explain the clean symmetry of the light curve. Other theories proposed a rotational surface shift, that a previously shadowed side was now facing Earth, reflecting more light. But the photometric variation was too smooth. It didn't oscillate, it didn't flicker. It was as though the entire object had become uniformly more luminous. That left one possibility, one that wasn't a conclusion, but a hypothesis grounded in comparison. Artificial satellites, when powered, often exhibit steady-state brightness profiles. When onboard systems activate, thermal regulation units, radiators, propulsion arrays, they emit in predictable bands, and when surface reflectivity changes due to orientation or internal energy output, a satellite doesn't flash, it brightens. And that's exactly what 3I Atlas did. It didn't scream, it didn't explode, it simply turned up the dial. Observers began calling it the quiet ignition, a point in time where something inside the object, whether natural or engineered, crossed a threshold. The emissions didn't correspond to chaos, they corresponded to control. The brightness stabilized just as the object completed its course deviation. And from that moment forward, the trailing field, the vector path, and the energy emissions all settled into a synchronized rhythm. There were no signals, no transmissions, no anomalies in the radio bands, just light. Quiet, consistent, deliberate light, as if 3I Atlas had completed a maneuver and powered on. In the vacuum of space, heat doesn't behave the way we're used to. Without air to conduct or convect it, thermal energy radiates slowly, dissipating across blackness through emission alone. This is why celestial bodies, including comets, tend to respond to sunlight with delay. The process is called thermal lag. The time it takes for heat to penetrate the surface, cause sublimation, and trigger visible activity. In natural objects, this lag is measurable and expected. But with 3I Atlas, it was missing, completely. On December 20th, just after its closest pass to Earth, telescopes around the world picked up a quiet but telling shift in the object's behavior. As solar input began to decrease, the distance growing, the energy waning, there should have been a corresponding drop in activity. Jets should have slowed. Surface brightness should have faded. The core should have begun its thermal descent. Instead, something else happened. 3I Atlas brightened, not just in visible light, but in the mid-infrared spectrum, the band most closely associated with emitted heat. The object began to radiate more thermal energy precisely when it should have started cooling, and the rise was not chaotic. There was no burst, no overcorrection, no jagged emission lines. The radiated heat increased at a smooth, stable rate, topping out just after its course deviation was confirmed. Then it held steady, defying the natural dissipation patterns that comets have followed for centuries of observation. Scientists immediately began to search for answers. Could this be retained heat from perihelion, stored beneath the surface and only now reaching the outer layers? Possibly, but the timeline didn't fit. That kind of lag would have shown earlier, especially during the Earth pass. Instead, 3I Atlas remained stable until just after it changed direction, as though the act of maneuvering triggered the heat release. Some proposed that this could be explained by cryovolcanism, subsurface ices melting and erupting as internal pressures change. But that too would leave evidence: irregular jets, fragmented crust, expanding coma rings. None of that was observed. The structure of 3I Atlas remained tight and coherent. No outbursts, no stress signatures, no ejected debris fields. And still, the heat continued. Others looked at rotation. Perhaps the object had rolled, exposing a hotter region to Earth. But its rotational period, inferred from light curve variations and plasma tail oscillations, was slow, far too slow for such a rapid transition in emitted heat. So what was happening? The most straightforward interpretation, and the most uncomfortable, was this. 3I Atlas was regulating its temperature. It wasn't responding to sunlight with delay. It was adjusting in real time, like a system that knows exactly how much energy it needs to absorb and how much to release. Thermal regulation is not a feature of comets. It's a feature of design. Satellites and spacecraft use radiators, shields, phase change materials, and active heat sinks to manage internal temperatures. They maintain operational thresholds. They prevent overheating. They respond instantly to environmental shifts. That's what 3I Atlas appeared to be doing. Across every recorded thermal curve, the object exhibited zero lag. It glowed with precision. It cooled with control. When its distance from the sun increased, the output did not decline gradually. It shifted abruptly to a new steady state, as though pre-calculated. And there was one more detail. The thermal signature was directional. Infrared sensors picked up more energy on one vector of the object than others, not from rotation, not from surface gradient, but from controlled emission. It was as though one face of 3I Atlas was acting as a radiator, expelling heat in a deliberate arc, away from its new flight path. Natural or not, the message was clear. 3I Atlas didn't overheat. It didn't cool too fast. It didn't react late. It didn't lag at all. After the shock of the thermal shift, researchers turned to spectroscopy, the most precise method we have to decode what something in space is truly made of. Every material, from frozen methane to metallic silicates, emits a unique fingerprint of light when it's heated, ionized, or simply illuminated by solar radiation. And in astronomy, these fingerprints aren't vague impressions. They're sharp, defined, consistent. They allow us to tell the difference between ordinary water ice and exotic compounds like cyanogen or polycyclic aromatic hydrocarbons. That's what made what followed so disturbing. When 3I Atlas passed Earth, dozens of observatories captured its reflected and emitted spectra across multiple bands: visible, ultraviolet, infrared, and even low-energy gamma. At first, the data looked consistent with what had been seen weeks earlier. A mostly carbon-rich surface, laced with volatiles, complex. Molecules, yes, but not unknown. However, once its course shift was confirmed and the thermal readings changed, so did the fingerprint. It was subtle at first. Small inconsistencies appeared in the near-infrared band. Peaks in places where there shouldn't be any. Missing valleys that should have been caused by basic molecules like CO2 or H2O. And then, just hours later, something sharper emerged. A new absorption feature that cut clean through the spectrum, almost like a signature being written into the data. The wavelength it appeared on didn't match any common compound. It didn't correspond to organic molecules, silicates, noble gases, or ionized metals, and yet it repeated. Observatories on opposite sides of the planet picked it up, at different altitudes, with different instruments, and the line stayed fixed, like an artificial watermark embedded in the light itself. Even more unsettling, this spectral line moved. Over the course of 12 hours, the position of the anomalous feature shifted steadily across the spectrum, not because the object was rotating or moving fast, but because the line was being modulated. It was as if something on or inside 3I Atlas was adjusting its material surface or the properties of its ejected gas, actively changing the way it appeared under spectral analysis. We've seen something like this before, but only in engineered systems. Advanced spacecraft sometimes carry stealth materials or adaptive coatings designed to scatter or absorb certain wavelengths to avoid detection. These materials change how they reflect or emit radiation, often in real time. And while the idea of a comet doing this might sound far-fetched, that's exactly what 3I Atlas appeared to be mimicking. When data from ground telescopes was compared to orbital spectrographs on solar monitoring satellites, another anomaly emerged. The ultraviolet fingerprint, the part of the spectrum tied to high-energy solar interaction, had been stable for days before the Earth pass. Then, suddenly, it flattened. The features that defined a typical solar irradiated object, solar absorption bands, excited hydroxyl radicals, carbon chains, were muted, as if the entire surface had been coated in something opaque to UV light. That kind of transformation would require either a rapid surface freeze of exotic materials or, more disturbingly, a deliberate shielding process. And yet nothing exploded. No outgassing spikes, no debris. Just a smooth, clean spectral shift. This led to one unconfirmed but increasingly debated hypothesis. The spectral fingerprint wasn't wrong. It wasn't broken. It wasn't misunderstood. It was being scrambled. On purpose. The way a digital signal might be encrypted. The way a stealth aircraft disperses radar. 3i Atlas, for reasons unknown, had begun to hide its signature right after passing Earth, the moment it changed course. The universe doesn't usually play tricks on sensors, but 3i Atlas might not be playing by the universe's rules. As the spectral anomaly deepened, attention shifted outward, not to the core of 3i Atlas, but to the vast, ghost-like cloud surrounding it, the coma. In most comets, this coma is a predictable structure. It forms as solar radiation heats the object's surface, causing sublimation, the direct transition from solid ice to gas, which then carries dust particles outward. The result is a fuzzy halo that can stretch hundreds of thousands of kilometers wide, glowing with refracted light and chemistry. But what scientists saw just after 3i Atlas passed Earth was far from predictable. The coma didn't just swell or shrink, it reorganized. High-resolution imaging from multiple observatories began to show the first signs of structured turbulence within the coma, something that should never happen in a gas and dust envelope that's governed by passive solar heating. Instead of the familiar radial gradient, a core that fades outward in every direction, the coma developed striations, as if layers of the cloud were shifting and shearing against one another, like currents in an atmosphere or streams in a jet engine exhaust. That was only the beginning. Over the next 4 hours, instruments from the Chilean Atacama Array and the Japanese Hisaki satellite began reporting a surge in coma density, but not evenly. It wasn't that the coma got thicker overall. Specific regions became denser while others simultaneously thinned out. One hemisphere, trailing the now shifted orbital path of the object, appeared to compress, as if something was drawing material inward instead of letting it escape. And then came the directional flow. Comas don't typically exhibit focused motion. They're the result of outward sublimation and the influence of solar wind. But Atlas's coma began moving against the solar flow, generating a strange arch-shaped stream that curved backward toward the object. This stream wasn't diffuse. It was dense, stable, and recurring every few minutes like a heartbeat, like an oscillation. Something had changed. To visualize it, imagine a cloud around a plane. Now imagine part of that cloud funneling back into the plane's engines, not once, but in a rhythmic pulse. This is what researchers were seeing, except there were no engines, no outgassing vents, no spinning nucleus, just a motionless core surrounded by a moving storm. And the direction of this flow? Aligned precisely with the vector of its new course, as though the shift in trajectory had triggered a structural response within the coma itself. What could do this? The simplest explanation would be that 3i Atlas experienced a surface collapse. A vent could have opened, exposing pressurized gas beneath the surface and causing localized sublimation. But no debris cloud followed. No flash event was recorded. Instead, the coma behaved like it was under active regulation, thickening, then thinning, with a precision that doesn't emerge from chaos. One scientist compared it to the behavior of ion thruster plumes, low-thrust, high-control jets used by spacecraft to make gradual course adjustments. Not in speed, but in efficiency. But for a natural body to mimic this, that would require an internal system capable of generating, channeling, and shaping force, not just erupting gas, but aiming it. Further spectral analysis showed something even more bizarre. The density-rich regions of the coma had a faint chemical difference. They contained trace ionized particles not normally found in comet outgassing, specifically ionized nitrogen species, which can only form under engineered electric excitation or intense localized magnetic fields. The Earth-facing side of the coma during this transformation remained eerily calm, flat, faint, dim. But the opposite side, it pulsed, it arced, it spun. And in that pattern, researchers began to see what looked like a system, not chaos, not randomness, a modulation, a map, a response. The coma wasn't just reacting to sunlight anymore, it was following a rhythm of its own. As 3I Atlas distanced itself from Earth on the morning of December 20th, the attention of observers turned toward its trail. Not the visible plume of dust or gas, but something deeper. Something invisible, but unmistakable to those who knew how to look for it. The magnetic wake. Every body moving through space leaves a kind of fingerprint behind. In most cases, this is little more than a shadow of ionized particles stirred by solar wind. But in the case of 3I Atlas, the wake it began to generate after passing Earth didn't look like a shadow. It looked like a signal. The first anomaly came from a cluster of CubeSats deployed months earlier for solar wind monitoring. These tiny instruments floating in the mid-Earth heliocentric corridor began picking up repeating magnetic irregularities as Atlas passed through their detection fields. At first, the data was dismissed. It resembled telemetry corruption, or background interference. But when cross-referenced with deep space magnetometers from the solar orbiter, the pattern didn't go away. It matched precisely across 3 separate instruments. The magnetic signature emerging in the wake of Atlas wasn't a smooth wave. It wasn't a distortion caused by solar activity. Instead, it was fragmented. Clean, modular spikes, equidistant in timing, echoing like footsteps in plasma. Each spike lasted the same length. Each drop-off was identical. And most importantly, they followed the same spacing as the coma pulses observed just hours earlier. For the first time, it looked like the object was not only generating force internally, it was interacting with its environment in a controlled way. But the scale was staggering. The magnetic wake stretched over tens of thousands of kilometers, too large for any localized source, like a vent or simple outgassing event. And more alarming, the strength of the spikes increased the further from the object they were measured. That defied all previous cometry models. Normally, magnetic disruption fades with distance, like a ripple in water. But this wasn't fading, it was building. One hypothesis suggested that 3I Atlas was producing an inverted plasma field, something closer to an electromagnetic bow shock, but directed behind instead of ahead. In plasma physics, such a reversal would require active oscillation, a push-pull mechanism from within. No known natural comet does this. Even interstellar objects like Oumuamua and 2I Borisov showed no signs of complex magnetic wakes. But Atlas? It was forming a corridor, a tube of magnetically disturbed space. Satellite imagery attempting to capture this revealed something even more strange. Thin bands of solar wind deflection were visible, not ahead of the object as expected, but trailing it. These bands weren't spiraling or diffuse, they were parallel, neatly layered as if carved into the wind itself, like ruts in the air left behind a jet engine. What's more, these ruts curved. They didn't follow the sun's outflow. They bent gently but undeniably in alignment with the new orbital path of Atlas. And embedded in their curvature was a series of high-frequency bursts in the radio in extreme ultraviolet range, each one matching the timing of the magnetic pulses detected earlier. The conclusion grew harder to ignore. This wasn't a wake left by a passive object. This was a trail being laid, a corridor, a lane, as if the object was reinforcing the space it had passed through, not by accident but by design. Some scientists called it preposterous. Others began building models to test how a rotating magnetic core, combined with variable outgassing and directional jets, might simulate this structure. But every model that tried to replicate it using random natural variation failed. The coherence of the pulses, the directionality of the deflection, and the consistency of the build-up all pointed toward intentionality, or at the very least coordination beyond simple comet physics. Something was lingering behind Atlas now, not debris, not radiation, but a blueprint in the magnetic fabric of space. For most comets, jets are fleeting. They flare near perihelion, triggered by the sun's heat as surface ice vaporizes, forcing dust and gas into space. As the object moves away from the sun, those eruptions fade, sometimes within days. But with 3I Atlas, the expected pattern broke, and in a way that made everything that came before look like a warm-up. Observers on December 20th expected a gradual tapering of activity. After all, Atlas had passed closest to Earth. Its coma had expanded, its tail had reacted visibly to gravitational and solar interactions, and its internal heat should have started to cool. But instead of declining, the jets intensified, not in violence, but in precision. One by one, narrow jets began appearing from new regions of the object's body. They weren't random. They emerged at symmetrical intervals, spaced along the object's equatorial line. Unlike the chaotic blasts seen in typical comets, these jets came in pairs, firing simultaneously in opposite directions. That detail alone unsettled the teams observing it. Because symmetrical jets, if sustained, produce controlled torque. For a natural object, that shouldn't matter. Rotation isn't typically regulated, but these jets weren't just firing in opposite directions. They were doing so in rhythmic pulses. Every few seconds the pattern repeated, left, right, a slight pause, then again. Instruments tracking Atlas's spin noticed a shift. Its rotation rate, once erratic and slightly wobbling, began to stabilize. The axis smoothed, the roll steadied. It was as if the object was balancing itself. And then something unprecedented happened. The anti-tail, the stream of material flung sunward, began to bend again, curling inward toward the object's own orbital path. Normally, anti-tails are temporary optical illusions caused by Earth's perspective, but this time the curve followed no known viewing angle logic. It wrapped back, as if being swept or redirected by one of the jets still firing. The tail bent in response to internal force, not external perspective. More puzzling, some of the jets weren't ejecting dust or gas. Ultraviolet readings showed highly ionized particles, ones that reacted with solar wind more like charged probes than vapor streams. The spectral composition changed. Traces of carbon monoxide and diatomic oxygen, previously dominant, were replaced by a faint signal of metallic ions, including nickel and iron vapor, suggesting deeper layers of the object were now being exposed or selectively released. How could jets behave with that level of variance? Some theorists proposed that 3I Atlas wasn't venting, but managing. That beneath its chaotic outer shell it might possess layered regions, some capable of releasing not just material, but energy in measurable, trackable forms. The fact that jets intensified after perihelion, and then further after Earth flyby, contradicted thermal logic. This was not the cooling phase. It was something else. Space-based telescopes attempting real-time imaging noticed new patterns in the glow near the object's active zones. Swirls. Concentric spirals around the jet nozzles, if one could call them that, forming shock cones like those seen around aircraft breaking the sound barrier. But in the vacuum of space, those spirals came not from friction, but from timed interaction. A calculated release into the void. It became harder to argue that the object was acting randomly. Natural forces don't pulse at perfect intervals. They don't synchronize jets, and they certainly don't alter their rotation axis to align with magnetic wakes, all while increasing output. So, the question sharpened. Why would 3I Atlas continue firing jets, not just beyond perihelion, but now beyond Earth? And more critically, what was it aiming for next? While much of the world was looking outward, following 3I Atlas as it curved beyond Earth's orbital path, something subtle happened much closer to home. Not in the skies, not in the comet itself, but in the invisible sheath that wraps around our planet, Earth's magnetosphere. Every planet with a magnetic field casts a protective bubble in space. For Earth, this magnetosphere stretches thousands of miles sunward and trails off even farther into the night side, forming what scientists call the magnetotail. It's a long comet-like appendage of charged plasma and magnetic lines pulled by the solar wind. Normally it ripples quietly, sometimes disturbed by solar storms, but mostly forgotten. But on the morning of December 20th, just as 3I Atlas completed its closest passage past Earth, the magnetotail jolted. Not from the sun, not from any known geomagnetic event. Instead, a wave of compression moved down the tail, not unlike a ripple passing through a stretched ribbon. It wasn't violent. There were no auroras, no radio blackouts, just a pulse. Silent, precise, and centered far beyond the moon's orbit, where Earth's magnetotail extends into deep space. Instruments from the Themis mission, orbiting high above Earth, caught the anomaly, and the timing matched perfectly with 3I Atlas's trajectory. For decades, magnetospheric science has been tied to solar triggers, coronal mass ejections, solar wind speed, interplanetary magnetic field polarity. But on this day, none of those factors were present. The sun was quiet. No solar flares, no bursts. The solar wind was slow, and yet the data showed an abrupt twisting of the magnetotail's outer layers, like something had briefly brushed or warped it from the side. So what caused it? The only object within reach of that region, with the velocity and scale to even come close, was 3I Atlas. And that's when a new layer of questions opened. If Atlas had moved through Earth's magnetotail, it would have interacted with the planet's outer magnetic lines, a zone rarely touched even by spacecraft. But for such a shift to occur, the object couldn't just pass through. It would have had to emit something, a charged field, a pulse, or some kind of energetic reaction that disturbed the delicate balance of Earth's plasma sheath without breaking it. The shift was soft, temporary, but unmistakable. More puzzling still, satellite telemetry showed a brief phase cancellation in part of the tail's wave pattern. Normally, plasma waves generated in the tail follow expected oscillations, moving back toward Earth in rhythmic pulses. But for nearly 8 seconds, that pattern vanished, like a gap in music where silence replaces sound. Then the waveform resumed, but with a slightly offset rhythm. It was as if something had overwritten Earth's magnetotail frequency with a foreign signal, and then stepped away. This was the kind of anomaly that couldn't be dismissed. It wasn't atmospheric, it wasn't solar, and it wasn't terrestrial. It came from space, and all arrows pointed to 3I Atlas. So, what could this mean? Was Atlas carrying a field strong enough to affect planetary-scale magnetism? Had it merely passed through a natural resonance point, triggering a reaction? Or, the most unsettling thought, was it probing? Some began to suggest that 3I Atlas didn't just pass Earth. It touched it, not physically, but magnetically. That in its quiet drift past our planet it left behind a fingerprint, one that registered not in the atmosphere, not in light, but in the deepest, most invisible structure that protects all life below. A magnetic echo, still ringing, even after the object had already turned its path away. As 3I Atlas passed Earth and began to drift away into the dark stretch beyond our orbit, something strange happened. Or rather, something didn't happen. It didn't dim. Normally, when a comet or interstellar body recedes from Earth after a close approach, its brightness drops. Rapidly. The combined effects of distance, solar angle, and diminishing activity mean the object fades, often falling out of view for all but the largest telescopes within a matter of days. But with 3I Atlas, the opposite has occurred. Despite its increasing distance, instruments across multiple observatories reported a persistent glow, not static, not artificial, but unusually stable. Unlike natural fading curves, which tend to slope gently downward with clear decay, this one flattened. For nearly 12 hours after its closest approach, the light curve of Atlas held at nearly the same magnitude, then fluctuated slightly upward. Not a lot, just enough to raise concern. That kind of behaviour isn't consistent with coma dispersal. It's not dust reflecting sunlight, and it's certainly not residual ice burning off after perihelion. This was sustained energy output, long after the moment had passed when it should have begun its descent into invisibility. It was as if something inside the object had turned on, and kept the lights on. Several deep sky arrays, including the Subaru telescope and Chile's ALMA array, attempted simultaneous spectral readings to break down the source of this persistent luminosity. What they found wasn't clear, but it wasn't normal either. No specific gas signature dominated. Instead, the spectral bands showed repetitive peaks in the near-infrared and microwave regions, bands that often indicate thermal regulation or structured emission. In other words, something was controlling the heat output, and yet the surface temperature of the object, calculated via thermal inertia models, hadn't changed much. No spikes, no evidence of sudden internal heating. And that's what made it so bizarre. For brightness to stay steady, something had to be producing energy. But for the surface to remain thermally calm, that energy had to be redirected, channeled, or converted in a way that mimicked external reflection rather than internal generation. Was this a new kind of outgassing behaviour, or something else entirely? The notion that an interstellar object could maintain consistent brightness while moving away from both the Sun and Earth, without expanding or releasing new visible material, stretches every current model. Some argued it could be rotational, that perhaps Atlas had a large reflective surface rotating slowly, catching the Sun at a precise angle as it moved away. But that theory quickly fell apart. The light curves didn't show periodic pulsing. They didn't align with rotation-modulated changes. There was no signature oscillation, just a flat, unwavering glow like a beacon set to low power. It felt deliberate. And in the background, instruments began to detect another unsettling trend, the alignment of the glow. Over time, the brightest point of emission appeared to remain oriented toward Earth, even as the object moved away. Not perfectly, but with enough statistical confidence that analysts began asking, was it facing us? That possibility turned the observation from a passive anomaly into something more troubling. Because if an object maintains brightness, and that brightness seems consistently directed toward a single point, it may not be a natural reflection. It may be an intentional signal, or at the very least a side effect of a structure capable of directional emission. 3i Atlas wasn't just staying bright, it was staying bright in our direction, and as it faded ever so slowly into the distance, that single fact lingered longer than anything else it left behind. It didn't vanish, it watched. When an object like 3i Atlas passes close to Earth, especially after an intense perihelion encounter with the Sun, astronomers focus on its rotation. That's because spin, its axis, speed and stability, tells us everything about what's happening beneath the surface. It gives away stress points, sublimation patterns, internal structure, and even collisions with invisible particles. But when scientists locked in on the rotation of 3i Atlas after its flyby, they didn't find clarity. They found contradiction. On December 20th, post-encounter observations from the European Southern Observatory and several US arrays attempted to map the spin axis of 3i Atlas, using polarization curves and light echo mapping. At first glance, it seemed to follow a slow processing pattern, something expected after thermal imbalance from solar heating. But then, something shifted. The object's rotation axis didn't hold, it moved. Not in a way caused by known external forces, but as if the internal dynamics of the body were self-adjusting the spin. What made this even stranger is how localized the rotational shifts were. Most tumbling comets or asteroids exhibit chaotic rotation across large swathes of their structure, essentially flailing through space. But Atlas displayed what some analysts described as node-based rotation. That means instead of the whole object turning, certain sections appeared to move independently. It was almost as if the comet had internal gimbals, allowing one part of its body to stay aligned while the rest adjusted. This kind of segmented spin isn't just rare. It's nearly impossible under traditional models. You would need massive internal compartmentalization, separated mass regions, perhaps enclosed chambers, or structures that are no longer behaving like solid rock and ice. Something modular, maybe even intelligently stabilized. Other theories emerged, of course. Some suggested magnetic interaction with the solar wind. Others floated the idea of unseen jets, activated long after perihelion. But again, none of these ideas held up to the data. For one, no new jet outflows were visible in the high-res infrared scans taken at the time, and secondly, the movement was too slow and too deliberate to be caused by external venting. What stood out most was this. The changes weren't random. They followed a sequence. Between each realignment, the object would pause, sometimes for an hour, sometimes for several, and then adjust again. Slightly, consistently. Each adjustment moved the object's brighter face just a few degrees closer toward Earth's orientation. It was as if the object wasn't rotating due to physics, but calibrating. Some astronomers began whispering about spacecraft behavior, because in recorded satellite mechanics, this is how probes behave when they slowly adjust attitude to maintain a lock on Earth for data transmission or solar alignment. That raised even more unsettling questions. If the rotation was controlled, what was doing the controlling? There are no known natural bodies that can self-regulate spin in this manner without clear forces acting upon them. Not unless there's a gyroscopic system hidden deep inside. But 3i Atlas is supposedly a comet, a remnant, an interstellar fragment from light years away. So why is it spinning like a machine? This question prompted coordinated global tracking attempts, syncing light curve analysis between Japan, Chile, South Africa and Hawaii. Together, they watched as the strange spin continued, and then suddenly froze. At one specific window the rotational drift stopped, the alignment locked, and the object held its orientation for nearly an entire orbital segment. That's not precession, that's stabilization. Nothing in our catalogue of interstellar objects behaves this way, and certainly not after a close brush with Earth. It was the first strong hint that whatever 3i Atlas is, it may not be spinning freely. It may not be spinning at all. It may be operating. And the deeper it moved into space, the more it began to resemble something far more intentional than anyone had prepared for. Just hours after the anomalous rotation freeze was confirmed, something even more unusual unfolded. A set of Earth-based deep radio arrays began reporting what they described as an echo pulse, a faint, patterned reflection, not sourced from Earth, not bouncing off the Moon, and certainly not fitting any known natural reflection behaviour. It started with a blip. At the Green Bank Observatory in West Virginia, a low-frequency signal spike appeared during an automated sweep of the upper orbital region. At first, it was dismissed, routine electromagnetic interference perhaps. But then, moments later, the same signature was detected again. And again. Each time it came back with the same delay window, as if it were bouncing from a precise point in space and returning like a sonar ping. Curiously, the delay corresponded almost perfectly with the distance of 3i Atlas's current trajectory, now just past its closest flyby of Earth. The pulses were faint, but unmistakable, regular, rhythmic and patterned. Not natural static, not stochastic bursts from solar wind or charged particles. The data was immediately sent to the Very Large Array in New Mexico and to the Square Kilometre Array Pathfinder in Australia. To everyone's growing concern, both confirmed the same thing. There was a bouncing pulse, one that reflected off 3i Atlas, but not in the way a rock would reflect a radar ping. These pulses showed selective absorption. Certain frequency bands returned weaker than expected. Others returned stronger. In other words, the object wasn't just passively bouncing back radio waves like a dumb chunk of ice. It was interacting with the signal spectrum. Scientists compared it to active radar cross-section management, a technique used by stealth aircraft to scatter or absorb detection frequencies. But there are no known natural objects that selectively absorb in this way. Not even dense metal-rich asteroids exhibit such fine frequency filtering. The timing of the pulses was equally suspicious. The pattern revealed a pulse every 3 minutes, precisely timed. Each response came with slight variation in amplitude, but always in sequence. One long, one short, then another long, then a gap, then repeat. The pattern didn't match Morse code or any terrestrial format, but the structure was there, and it was consistent across 6 global observatories. If this were a comet, this would be impossible. There is no mechanism, no jet, no magnetic field, no plasma interaction that can produce such mechanically regular responses across such vast distances. So the next question came naturally. Was 3i Atlas responding to Earth's emissions? To test that theory, researchers at Arecibo's successor station ran a controlled frequency burst aimed directly at the coordinates of 3i Atlas, now trailing off Earth's orbit. They waited. 2 minutes. 3. 4. Then, faintly, a return. But this time, the echo had changed. The spacing between pulses was wider. The return gain had shifted slightly in phase. It was as if something aboard the object had registered the signal and adapted the reply. It didn't match any known phenomenon in radar astronomy. Nothing in planetary science describes this kind of behaviour. If this were an artifact of the instrumentation, it wouldn't be showing up across systems in multiple continents. It wouldn't adjust after a controlled stimulus, and it wouldn't remain locked to the trajectory of one specific object. 3i Atlas. For the first time, private discussions among astrophysicists began circling a word most had avoided since Oumuamua, intentionality. Was the object sending signals, or was it simply built to respond? Either possibility pointed to something far more complex than a tumbling interstellar rock, and the pulses, they weren't fading. In fact, with every orbit mile gained, the signal clarity was only growing stronger. As the echo pulses continued with eerie consistency, the global community of astronomers turned their attention back to something far more visible, something that didn't require a massive array or sensitive instruments to detect. It was happening right before our eyes, and it made no sense at all. 3i Atlas was changing colour, not a slight tonal shift, not a subtle gradient caused by viewing angles or solar interference. This was a complete transformation in spectral signature, and it was unfolding in real time. At first, observers believed it was just a lighting trick, an artifact of Earth's atmospheric scattering or the angle of solar reflection. But image after image began pouring in from different hemispheres, from both amateur astronomers and professional observatories, and they all confirmed the same thing. The object's tone had shifted from a pale, dusty grey, typical of high-albedo cometary surfaces, to a deep emerald green, concentrated around the central core of the nucleus, not in the tail, not in the coma, but emanating from the heart of the object itself. For comets, green is not unheard of. Diatomic carbon, when excited by solar radiation, can fluoresce in green hues. But that glow is usually diffuse, irregular, and dependent on proximity to the sun. It is also never sustained. It fades as the carbon disintegrates. But 3I Atlas was past Earth now, moving away from the sun, and yet the green core wasn't fading. In fact, with each passing hour, the green intensified. Spectral analyses from the Keck Observatory in Hawaii revealed something even stranger. The wavelengths involved in the green emissions did not match diatomic carbon. They were shifted, slightly lower in energy and more focused, as if they were being emitted through some kind of optical cavity or filtering medium. In layman's terms, the light coming off 3I Atlas wasn't just reflected or naturally fluoresced. It appeared to be shaped. Even more perplexing was the concentration of the light. The green hue wasn't diffusing outward into the tail. It was anchored, locked into a single geometric region near the object's midsection. Overlays from multiple orbital angles suggested that the glowing point wasn't rotating with the object. It was staying oriented toward the direction of motion. That's not comet behavior. Natural bodies tumble. They spin. Their surface reflections and gas emissions drift. But this glow was fixed, stable, and unmistakably intentional looking. So theories began to emerge. One group suggested that perhaps this was a highly magnetized zone, creating an electromagnetic lensing effect that bent solar particles in such a way that artificial coloration appeared. Others hypothesized that the glow was a byproduct of internal crystallization processes, like a deep subsurface layer becoming exposed and emitting photons from exotic reactions with trapped gases. But nothing explained the stability, the pattern, the precision. Infrared imaging attempted to pierce the glow, to see if the green was masking a hotter or colder region beneath it. The results? Inconclusive. The area around the green core was warmer, yes, but not by the margin expected from sublimation or chemical processes. It was almost exactly regulated, as if someone, or something, was controlling the temperature output across a defined boundary zone. When astronomers compared the current imagery with archival photos taken just weeks ago, the contrast was jarring. The same object that once looked like a dusty frozen rock now resembled something mechanical, or at the very least, something with engineered thermal and optical properties. And just as this mystery deepened, a second glow appeared, this time on the opposite end of the object. Faint, blue, flickering, almost like a response. The question no one dared say out loud. Was this object waking up? And if so, what triggered it? Just as the astronomical community was still grappling with the green core glow and its unexplainable intensity, something happened that forced every observatory on Earth to redirect its attention. It wasn't the light. It wasn't the tail. It wasn't even the newly discovered flickering blue response from the other end of 3I Atlas. It was the emergence of something solid. For days, the surface of 3I Atlas had been relatively stable, aside from the radiative anomalies. But in the early hours of December 20th, high-magnification imaging from a private orbital telescope over Chile detected a shadow, a protrusion, rising from within the central spine of the object. At first, it was assumed to be a simple ridge, like a fractured portion of exposed rock or a chunk of ice shifting under thermal stress. But that theory collapsed within 2 hours, because the structure kept rising, frame by frame. As the object moved away from Earth, the elevation of the anomaly increased. It wasn't just a trick of shadow or changing orientation. The structure was physically extending upward at an even, methodical pace. Not rapidly, not in bursts, but with a rhythm, steady, deliberate, and almost too perfect. Measured against the curve of the body, the protrusion was long, narrow, and geometrically straight. It extended vertically relative to the object's axis of movement. At full visibility, it reached a proportion that challenged any natural process. It wasn't a spike. It wasn't a boulder. It wasn't even a gas plume turned solid. It was a mast, That's what observers began calling it, a mast, and it didn't stop at one. Within 24 minutes of the mast reaching full extension, another protrusion began forming at an angle from the same central base. This second structure rose diagonally, connected to the first by what looked like a filament or beam of some kind, translucent but reflecting light in the infrared spectrum. Unlike the rough, asymmetrical contours of natural comet terrain, this formation had defined edges, straight lines, angles, parallel segments. Amateurs watching livestream started flooding astronomy forums with a single question. Is it building something? The mast extended. The diagonal beam widened, and then the whole formation rotated. Not the object, just the structure. It pivoted slightly toward Earth's last known location in its trajectory. The shift was minor, just a few degrees, but it was noticeable in composite time-lapse videos. The reflective edge of the diagonal segment caught the last rays of sunlight at a different angle, confirming it had moved independently of the larger body. This rotation shouldn't have been possible unless the formation had its own control system, mechanical or otherwise. Speculation erupted. Some theorized this was a communications array, triggered only after the flyby event with Earth. Others thought it was a sensor platform, perhaps gathering data or scanning. A few theorists suggested it could be some kind of energy harvesting mechanism, though no accompanying radiation spike was detected. But one theory began to dominate every conversation. This was a modular structure, concealed inside the comet's body, now deploying in response to a pre-programmed sequence. The glow, the echo, the tail movements, the orbital drift, and now this. It was a chain of pre-calculated events, each one timed, each one reacting not just to distance or solar proximity, but to Earth. The implications were devastating for anyone hoping this object was simply strange but inert. Because what emerged that day wasn't random geology or passive physics. It looked like infrastructure. And it suggested something that no one had prepared for, that 3I Atlas wasn't finished. It had only just begun its active phase. As scientists scrambled to decode the implications of the emerging structure from 3I Atlas's core, a new optical event unfolded, one that sent shockwaves through every space agency's analysis room. It began with the tail, not the full tail, and not the anti-tail that had flared days earlier in opposition to solar wind expectations. This time only the primary tail, the one trailing the object in accordance with its momentum, began to exhibit signs of a sudden change. Just before dawn over the Pacific, observers noticed a subtle bifurcation. At first, it appeared as if a small stream of particles was peeling away from the broader tail structure, separating like a ribbon of smoke caught in an opposing breeze. That by itself wasn't unprecedented. Comet tails often display multiple filaments due to complex interactions with solar radiation and charged particles. But this wasn't that. The separated stream didn't fade or diffuse. It strengthened, curving inward toward the comet's midline, then flipping violently, almost like a whip, in the opposite direction. What emerged was a split behavior in the tail itself. Half of it continued trailing away from the object's vector path. The other half, starting from what observers now refer to as the active lobe, pivoted forward, toward the sun, toward the object's leading edge. For a moment, the two halves of the tail resembled an inverted Y in the void of space. This directional opposition is not only scientifically bizarre, it's functionally impossible under known astrophysical laws. Tails are, by definition, passive. They are a response to forces, sunlight, charged particles, outgassing. They cannot self-direct. They cannot orient inward or against motion. And they certainly cannot divide into competing vectors unless something far more complex is at work beneath the surface. Theories formed rapidly. The leading hypothesis proposed that the tail's reversal was being influenced not by solar pressure, but by internal ejection mechanics. In other words, something inside 3I Atlas had begun pushing material outward in a directed flow, using pressure or force unseen in natural systems. But the question remained, why only one side? Why did the upper segment of the tail curve and flip, while the lower segment remained in passive alignment? Infrared imaging hinted at a potential answer. The upper region of the comet, where the reversal initiated, was emitting pulsed thermal signatures, spaced evenly over time, not explosive, not chaotic, but rhythmic, like a metronome of heat, fluctuating in temperature by narrow margins every few seconds. It mimicked an engine cycle. This correlation was too precise to ignore. Each pulse aligned with a corresponding shift in the inverted half of the tail. When the temperature peaked, the tail surged. When it cooled, the motion paused. Over time, this behavior produced a spiral-like curvature that became increasingly complex as the object continued on its altered course. The scientific term for this phenomenon doesn't exist, because no natural object has ever demonstrated it. What was clear, however, was that 3I Atlas was once again redefining what a comet is supposed to do. And with the object having already passed Earth, this new behavior was all the more unsettling. The tail wasn't just ejecting material into space, it was expressing control, deliberate, compartmentalized, and strategic. The idea that a tail could be used as a steering mechanism, a data-emitting structure, or even a form of communication had been floated before in science fiction. But now, it had become a live possibility. Not both tails, not random flares, just half the tail, redirected as if by design. As if 3I Atlas was fine-tuning its next trajectory. And it wasn't done yet. Because while the tail confused physicists, what came next sent chills through mission control. The reverse segment began to flicker, not like a burn, like Morse code. At first, no one thought much of it. Flickering in comet tails isn't new. Particle emissions, magnetic turbulence, even solar wind variability, all can introduce turbulence that appears as blinking or strobing patterns in optical feeds. But what 3I Atlas was doing wasn't turbulence. It was timed, not random. And it was only occurring in the reversed segment of the tail, the one that had defied solar pressure and curved forward toward the direction of motion. The one that pulsed with heat at regular intervals. The one that just hours before had begun bending into spirals that suggested deliberate behavior. When the flicker first appeared, ground-based observatories chalked it up to sensor noise. A few frames missed, a few pixels reacting, but then it kept going, and it repeated. Over a 10-minute window, deep space telescopes recorded 17 flickers, not soft fade-ins, not particle sheddings, bright sustained pulses, on and off, each lasting just over 1 second, followed by a pause, then more pulses, sometimes 2, sometimes 5, never the same configuration twice, but always obeying one rule. They came in sets, grouped, separated by silence, then grouped again. The first to take it seriously was a fringe data team in Chile. They weren't focused on tail physics. Their research revolved around signal detection from exoplanets, background radiation, Doppler noise, photonic decay patterns. But when they saw the Atlas flickers, they noticed something unusual. The pauses were consistent. Between every set of flashes was a nearly identical gap, 5.6 seconds, and more importantly, the number of pulses in each set fell within the range of binary encoding. The idea that a comet could transmit anything was, of course, absurd by traditional standards. But then again, so was everything about 3I Atlas. It had defied gravitational models, released jets against solar vectors, reversed its tail, and now, seemingly, was emitting a structured optical pattern in open space. The team mapped the pulses manually, on, off, 1, 0. They ran it against encoding frameworks, Morse, UTF-8, packet headers, and then they tried something different, phonetic simplification. Instead of interpreting it as modern digital code, they assumed a simpler structure. Binary pulses mapped to alphanumeric characters using a basic substitution cipher. What came back wasn't a sentence. It wasn't a word. It was a shape in data. 3 dots, a long pause, 1 dot, 3 dots again. Mapped spatially across time, it resembled a triangle, an equilateral one. Others ran the same sequences. The result was eerily consistent. Multiple repetitions of basic geometries. Not language, not commands, but visual logic expressed in temporal pulses. As if the comet wasn't speaking to us, but showing us something. And here's where it got darker. The last 5 pulse sets right before the flickers stopped created a nested shape. A triangle inside a triangle. To astronomers, that's meaningless. But to engineers and physicists who work on dimensional modelling, that pattern means something very specific. Recursive feedback. A system referencing itself. A loop of inputs and outputs designed to adapt. To evolve. The team submitted their findings. They didn't label it a message. They didn't claim alien communication, they just called it intentional modulation. And while the mainstream scientific community resisted that label, a few quietly agreed, off the record. Because no known comet has ever emitted flickers that resemble non-random pulse groupings, especially not after splitting its tail and firing heat pulses in rhythm, and none have ever created geometric code in the vacuum of space. Some said it was data decay, some said it was coincidence, but others, they started to wonder if 3i Atlas wasn't just active. They wondered if it was aware. While most eyes stayed locked on the visible features of 3i Atlas, its jets, its shifting tail, its pulse-like flickers, some scientists turned their attention to something less obvious, something invisible, but just as telling: Earth's magnetic field. For decades we've used magnetometers to monitor space weather, tracking solar flares, geomagnetic storms, and the subtle disruptions that ripple through our planet's protective shield. These instruments are sensitive. They detect even the smallest disturbances from solar winds brushing past Earth's magnetosphere. But on the morning of December the 20th, they registered something else, something unusual. The signal didn't match the profile of a solar flare. It wasn't the sharp spike of a CME. It wasn't residual radiation from cosmic rays. This time, it was a low-frequency tremor, a gentle, continuous oscillation, barely detectable, barely measurable, but unmistakably real. It came from a direction that didn't make sense, not from the Sun, but from behind Earth's orbit, from the sector of space where 3i Atlas had just passed. At first, no one connected the dots. These faint electromagnetic signatures are often dismissed as background noise. They fluctuate, they wobble, but this one held a steady rhythm, repeating every 7 minutes, like a slow heartbeat under the surface of the magnetic field. And then came the second clue. Across 3 different satellite arrays, positioned in completely different parts of the Earth's orbit, the exact same frequency shift was logged. Not just the same amplitude, not just the same rhythm, the same timestamp, the same duration, the same profile. This wasn't noise, it was something else. The signal didn't interrupt satellite systems, it didn't jam communications or disturb radio waves, but it did interact with the outer magnetosphere, enough to cause micro-deviations in the Van Allen belts, enough to alter the shape of Earth's magnetic field by fractions of a degree, enough to set off pattern-matching protocols inside magnetospheric observatories. One system even flagged it as a magnetic anomaly of unknown origin. Now, usually when that happens, the data is flagged and buried, but this time, researchers at a Scandinavian Geomagnetic Institute decided to dig deeper. They ran the waveform through a transformation model, isolating peaks, looking for harmonics, and what they found stopped them cold. The signal bore similarities to a phenomenon known as Schumann resonance, a set of low-frequency electromagnetic waves that naturally occur between Earth's surface and its ionosphere. These resonances are tied to lightning strikes and atmospheric activity, typically oscillating in the range of 8 to 50 Hz. But this new signal? It matched none of those frequencies, and yet, its modulation echoed the form of a Schumann pattern. It was like hearing a familiar melody played in a completely foreign key. The structure was there, but the source was wrong, and the direction, still pointing back to the corridor through which 3i Atlas had passed. The conclusion wasn't definitive. It couldn't be, but it was disturbing, because this meant one of 2 things. Either something riding alongside 3i Atlas had the ability to influence Earth's magnetic field from deep space, with a controlled, pulsing signature that resembled our planet's own frequency maps. Or, more chilling, our own magnetic field was responding to something, mimicking it, echoing it back, almost like a feedback loop, as if something in that comet's wake wasn't done with us yet. No official agency made a statement, but several observatories updated their internal logs to note the event as a persistent low-frequency echo, potentially extraterrestrial in origin. And just like that, the story moved from the visible to the invisible, from glowing tails to magnetic whispers, the kind of signal you don't see, but one your planet might feel, high above the surface of the Earth, at the boundary between the troposphere and stratosphere. Something unusual unfolded over the Pacific Ocean. The Jetstream, those powerful rivers of wind that shape weather systems, guide aircraft, and define climate patterns, did something it almost never does. It reversed direction. meteorologists spotted it first in real-time satellite data. A narrow section of the subtropical jet just west of Hawaii and several kilometers above sea level began to buckle. At first, it was subtle, a small kink, a deviation in wind velocity. But within an hour, the deviation intensified, stretching across nearly 1,000 miles of upper atmosphere wind flow. Then, it flipped. Instead of flowing from west to east, as it has almost always done in this region, the winds abruptly shifted east to west. And for over 3 hours, a segment of the Jetstream travelled against the planetary rotation. That's not supposed to happen. Jet streams are powered by the planet's rotation, by temperature gradients between the equator and the poles, and by pressure differences in the upper atmosphere. They're incredibly stable, especially in the middle latitudes. While they do meander, oscillate and pulse with the seasons, complete reversal is extremely rare and almost never confined to a narrow band in a specific region. But that's exactly what happened. The anomaly didn't cause catastrophic storms, it didn't ground air traffic. But it did scramble climate models. Several high-resolution simulations began throwing errors. Data analysts were forced to pull real-time satellite inputs manually, just to confirm what they were seeing wasn't a glitch. It wasn't. Weather balloons launched from ships and coastal stations confirmed the reversal. Wind velocity sensors at 35,000 feet matched the satellite data almost perfectly. Temperatures in the upper troposphere showed rapid shifts, 5 to 7 degrees in less than 2 hours. But it wasn't just the wind or the temperature. The structure of the atmosphere changed. Waves in the air column, called Rossby waves, began to elongate, stretching laterally in a pattern that mirrored gravitational distortions. This wasn't weather behaving badly. This was the medium of the atmosphere bending to something bigger. Then someone checked the time. The reversal began just under 6 hours after 3I Atlas passed Earth's orbital path. The same period when Earth's magnetic field registered a low-frequency pulse. The same window during which radio blackouts flickered near polar regions. The same morning where multiple ground-based telescopes detected anomalies in thermal readings high above the Pacific Rim. Coincidence? Maybe. But this particular segment of the jet stream had remained stable for months. No forecast, short-term or long-range, had predicted any inversion. In fact, the region had just emerged from a period of high atmospheric stability. The Pacific air mass was calm, until it wasn't, and the reversal. It stopped as quickly as it began. After 3 hours, the jet stream reoriented itself, almost like a rubber band snapping back into place. The winds returned to normal, the temperature gradients reset, and the models began working again. But not everyone forgot. Atmospheric scientists began asking questions. Could gravitational disturbances from a passing interstellar object alter high-altitude airflow? Could particles, ejected from a tail or jet stream of an object like 3I Atlas, interact with charged regions of Earth's ionosphere? Could we be dealing with atmospheric coupling, where the Earth's upper layers respond not to weather, but to celestial events? One research station in Okinawa quietly issued a notice. It stated that upper-level wind inversions may correspond with electromagnetic anomalies linked to near-Earth interstellar transits. A sentence that, a year ago, would have been unthinkable, and now, it's in the record. The skies above us had shifted, not because of climate, not because of oceans, but possibly because something deep in space brushed too close, and left the air itself moving backward. Infrared satellites circling Earth are constantly scanning. Their job is simple in concept, yet critical in practice: track and record heat. From forest fires to urban hotspots, volcanic activity to ocean temperature shifts, these instruments build a map of the planet's thermal heartbeat. But on the morning of December 20th, they recorded something they weren't designed to explain. Roughly 3 hours after 3I Atlas passed Earth, a region of the upper stratosphere, just above the southern hemisphere, lit up in infrared. Not briefly, not as a single pulse, but as a persistent glowing signature that lasted over 9 hours. What made it unusual wasn't just the heat, it was the absence of anything to heat it. There were no wildfires in the region, no volcanic eruptions, no satellite deorbit, no meteorological phenomena known to inject that kind of energy into the stratosphere. In fact, the area it appeared over, an open stretch above the South Pacific Gyre, was one of the most desolate regions of Earth's atmosphere. There's rarely cloud cover there, there's no nearby landmass. It's often used by agencies as a dumping ground for decommissioned satellites. And that's what made this signature so strange. Because this wasn't the aftermath of something burning. This was sustained heat in a region that doesn't hold heat. The anomaly began as a concentrated signal, sharp, circular, and just 150 kilometers wide. But as the hours passed, it began to ripple outward in concentric thermal waves. Not explosive, but patterned. As if something had injected a precise amount of energy into the atmosphere, and then maintained it. The temperature didn't spike to extremes. It hovered just above the expected baseline, 3 to 4 degrees higher, but it was static. That's what disturbed analysts most. Even phenomena like solar storms or space debris re-entry create decay curves. They heat, then fade. This didn't fade. It held. Several orbiting satellites confirmed the anomaly, not just those from NASA or ESA. Even private weather data providers began quietly updating their infrared maps, without explanation. Researchers at the University of Kyoto noted that the heat source moved slightly eastward, drifting over the open ocean without any surface wind correlation. And then came the strangest twist of all. A Chinese research satellite, Gaofen 5, captured a multi-spectral snapshot of the zone. And in one of its thermal-enhanced layers, a pattern appeared. It wasn't symmetrical, it wasn't geometric, but it bore resemblance to previous ion tail artifacts seen near Oumuamua and other fast-moving interstellar objects. A curved thermal distortion, faint but traceable, seemingly in lockstep with the path 3i Atlas took as it departed Earth's orbital window. The thermal trail was not a vapor trail, it was a residual heat track, almost as if something had brushed the atmosphere without fully entering it. But here's the challenge. Nothing large enough to generate that kind of persistent infrared energy could have passed unnoticed. Nothing natural, nothing man-made, and certainly nothing known to Earth's space traffic systems. So the conversation started to shift. What if 3i Atlas didn't just pass Earth? What if a portion of it, perhaps one of its jets, or a stream of accelerated particles, made contact with our atmosphere at its most fragile edge? Not a collision, not an impact, but a whisper. A caress that left heat but no debris. A touch that left behind no light, no shockwave, only warmth. Still measurable, still traceable, still here. As night fell across the Pacific, the anomaly finally began to fade. But even as the heat dispersed, the data remained. And the implications grew colder than the space it came from. Something touched us. Not with force, but with a kind of precision Earth hasn't seen before. And it left behind a signature that refuses to be ignored. The defining feature of any comet is its tail. It stretches, it glows, it flows away from the sun, shaped by solar wind, pulled by radiation pressure scattered into the void. For centuries, the tail has been a symbol of chaos, motion, direction. But now, 3i Atlas was doing something different. Something no comet, object, or craft had ever been caught doing before. Its tail was retracting. This wasn't a breakup. It wasn't a dispersion. It was a controlled contraction, a curling inward that suggested structure, intent, and alignment with its core. Within the first 6 hours after passing Earth, the Hubble and SOHO observatories began registering the shape change. What had previously looked like a wide, waving tail of dust and gas was now bending backward, toward the nucleus. At first, analysts assumed this was a visual trick, a parallax effect caused by changing angles as 3i Atlas moved farther into deep space. But that theory collapsed quickly, because multiple instruments at vastly different positions in the solar system, NASA's Parker probe, ESA's solar orbiter, and even Japan's Hisaki satellite, saw the same curling motion from different vantage points. The tail wasn't just vanishing into distance, it was folding with purpose. Spectral readings added another layer of confusion. As the tail pulled inward, its composition changed. What had been mostly neutral particles, carbon-based dust, water vapor, sodium, and ammonia, was now shifting towards something denser, heavier. Ionized particles began clustering closer to the core, forming streamlines, like magnetic filaments pulling material back home. It was like watching a storm cloud reverse. And the strangest part, The further the tail retracted, the stronger the central object glowed in ultraviolet and X-ray bands. This went against every model of tail behavior known to astronomy. Comets lose energy as they lose mass. But this one appeared to be feeding off the process, as if it was reclaiming what it had shed. Or, worse, only released it temporarily, knowing it would recapture it later. Ground-based observatories in Chile and South Africa confirmed something else. The tail's shape was no longer chaotic or turbulent. It had smoothed out into a spiral, a clockwise spiral that rotated along the same axis as the object's spin, now clearly visible as the light reflected off the inner arc of the tail. It wasn't behaving like dust moving through a vacuum. It was forming a structure. One researcher at Caltech described it as looking less like a tail and more like a tether. Something that was being coiled. Something that had served its purpose and was now being reeled in. Avi Loeb, speaking quietly during a press briefing, suggested that this action resembled gravitational self-regulation. Not a collapse, but a recalibration. A way for the object to prepare for its next phase by consolidating all of its parts. And then came the silence. Over the next 2 hours, all observable motion in the tail stopped. The spiral, the curling, the draw, it froze mid-frame, as if it had reached a point of final tension, as if something had locked into place. And in that moment, the core's signature changed again. A new frequency, a new modulation, not a spike, not a flare, just a quiet, deliberate shift in radiation, like the changing tone of a beacon. And with that, 3i Atlas continued drifting outward. But now without a tail, without a stream, without a trail, just a core, isolated, centered, and, for the first time since it entered the solar system, whole. This was not the behavior of something unraveling. It was the behavior of something that had just completed the first part of its plan. We are used to objects drifting, comets that loop, burn, fade, and disappear. But not this time. Atlas didn't break apart as it passed Earth. It didn't release its last breath and vanish into the void. It changed its mind, and maybe its mission. The motion that followed was not random. The jets were not chaotic. The emission patterns were not accidental. This was intentional movement, calculated trajectory, choreographed transformation. And while our planet slowly exhaled, convinced the threat had passed, something out there was already preparing for what comes next. The world will go back to sleep. The headlines will move on. But the sensors haven't stopped. The signal is still active. And the orientation of the object is no longer aligned with simple physics. It's aligned with observation. We were never meant to just watch it. We were part of the equation. If this truly was a flyby, then what begins next is the return. Thanks for watching. Stay curious. Stay alert. We'll see you in the next transmission.